we show you how to correct the grid line label in AutoCAD. After we import directly the file from AutoCAD, the label of the grid line is not shown. So you have to edit it, modify. You see here, this 0, the 2 0 is for the grid line. 1 2 3 4 5 6. Here 1. Take this out here. 1 2. Okay. 3. Okay. 4. Okay. 5. Okay. 6. Is correct. And for the grid line it's A, B, C. So we have to start from here. H is correct. Okay, is correct. A. No, it's not correct. It's A, B. Then this one is C. So now we have to complete to correct the grid line label. Okay. A, B, C, 1, 2, 3, 4, 5, 6. I have to show it again, and you have to check with your AutoCAD is correct or not. 1, 2, 3, 4, 5, 6. This grid line label A, B, C. Okay. Right. Okay. And now we have to show you how to do 3D structural element of the reinforced concrete by using easily rule of thumb. Let's start. Now we have to do 3D dimension of all the element, or the beam, or the slab, or the column, or the pie tab. Now let's start from the beam, and the overall height of the beam is equal to the length, total length of span divided by 10 or 55. Okay, so in the test the maximum span is 5 meters. So we start from here to here is 5 meters. So we will do the dimension of the beam. Now let's start with the 5 meters divided by 15. So the overall height of beam is 333. We take it 400 millimeters. So we take this because this section, to make sure it will be designed in simply reinforcement, and the deflection control is okay. Okay. So if you take the section is thin, then this recommend you will be designed and has a problem with the deflection control. So in this case you have to add more rebar percentage to issue the deflection. So to avoid the deflection problem, we have to take this rule of thumb, and the dimension of our section we take to 400 millimeter high and 200 millimeter width. Okay, letter width D and H. Okay, D and H. And for the slab we use the same L divided 82 to L divided 265, and the overall thickness is around 133. So we take 150 millimeter for the concrete. And for the minimum concrete compression strength. Compressive strength, you take it 25 megapascal for cylinder for structural element. Okay, and for the cover we take it the minimum is 30. Okay, so you have to check your span, which one is longer and which one is smaller, so you have to take from one span to another span to do equalization for the concrete slab and the concrete beam. But for the slab you have to check it. You will see here to here it has other beam, here to here other beam. But to make sure between this beam to the beam and between the beam to the beam, this area is not over this area. Okay, this area, this slab area is not over 30 square meter. Yeah? So it's over that area. We have to add other beam, okay, sub beam to support this area. Okay, in case it's over to support to 8 meter in the direction, so we have to add more beam. Okay, add more beam in other direction. So we will assume to make sure that the slab thickness is divided, follow the rule is divided on 35, but to make sure that the total area and span is not over 30 square meter. So it's over, you have to add more beam, okay, more support beam. So now we have to start to for the next step for the column. See here for the column. We have to determine the minimum concrete strength for the column 25 megapascal, but you can take it higher than this review. And for the surface load, can estimate it by use 1 pound or 2.3 pound per square meter to multiply with the area of column, area that column support and area of column support. So you will take each surface load, okay, because we take it from the previous tutorial, so to continue from that, you see here it is our rule assume we take it 1 pound per square meter multiply with you can check this rule assume from here, okay, to estimate the surface load, to predict the surface load on the pie tab or on our column. Here the total here, we take it from the joint and the tab, and we sum this reaction. You see here the total reaction, and the total area of the ground slab is here. We take it from the previous tutorial, you can check it. The dimension of the ground slab is 25 multiplied by 9 meter, and the area of one column is 5 multiplied by 4.5 meter. We check from here, okay, 25 multiplied with 9 meter. We take at the top of the ground slab only, and the area of supporting column is 5 multiplied with 4.5, okay, and the slab it has the total 4 slab in our model. You can check 1, 2, 3, 4, and for the 1 story on this 3, okay, 3, 1 story, 2 story, and 3 story, okay. And now you have to divide the total reaction load with the total area of the ground slab to take the review. is around 1.1 ton per square meter. Okay, so we can take the view from the 4 dimension in our pie chart or in our column, the column. We can take it from here 1, and you take it multiply with the area of the column and multiply with the story of the column. You will get the serviceability for estimation is around here 75 ton per column. So now we have to compare in the tab. Okay, then S. We check the reaction from our earlier assume. Now we have to run this again. You can do it quickly when you know the area or the supporting column with the story, okay, number story, and you can do it manually quickly. Okay, we will explain you more about this, and you can estimate the load in our PyCAD and to design our real PyCAD or our real foundation. Now we will verify this value with our real model which is correct or not. Then we assume or we take this value 1.1 ton per square meter multiply with the column area and multiply with the story. You will got this average, okay, estimated load per column for the serviceability 75 ton per column. Now we have to check for the serviceability. Okay, you can check here. Our real reaction is about 70, okay, 70 ton. But this not yet include the load of the stair. So in case you include the load of the stair, the value is we increase from here to over 70 ton. So you can take the value from here. It's around 70 ton per column. If it's clear, okay, that's clearly totally assume you can take it. Okay. Now we know that our column here is we take from here 5, okay, 5 for the column, okay, for the column 5 multiplied with 4.5, okay, it's 5 multiply 4.5. This is the column area, okay, and for we assume average load to estimate, we take it 1 ton per square meter multiplied by this value and multiply with the number story, okay, number of story is 1, 2, 3, okay, 1, 2, 3. So you can estimate that the average, okay, the estimate for serviceability load is around 67.5 pounds per column, okay. This is the quick method, okay, the quick method. You can use this method to predict the load on PyCAD or on our Pi, okay, on our Pi, to design your Pi during the capacity, to design Pi during the attachment, okay. This is a very quick clear method you can apply at the construction site. You don't have other data, you have only the story, you have only the column area, and you can take the value from, okay, 1 or 2, 1.3 multiply to that, you will get that issue, okay. And you compare with our earlier method, it is very similar, okay. Okay. And Now we can also estimate for the ultimate load in column. Okay, if you just to multiply with surface, okay, the estimate surface with 1.425, this value come from our zero code is 1.35 plus 1.5 divided by 2. The centimeter for this load, and then we take it the average centimeter from here to multiply for the ultimate load. Okay, so it will be increase from 1 to 1.425. Okay, for the ultimate. And now we have to estimate our column position. You first to determine the concrete strength. Now we have to put it the minimum one is 25 megapascal, and our clear section we have to estimate the clear section 200, 300, and now we can check here. We can check here. We have to check the maximum strength on our bottom column. Okay, you can check here. This for the ultimate load multiplied with the closest load area. Okay, you can see here the apply. This is the apply strength on the bottom of the column, and this one is the ultimate concrete strength. Okay, allowable concrete strength. So you have to make sure your concrete strength is over the applied strength. This is the basic concept. Okay, the applied strength to make sure your column is concrete working more than require the rebar. Okay, now if you choose this concrete strength to 20, what does it mean? The allowable concrete strength is lower than the applied strength from the column. So in this case, you have to design or to add more rebar section to increase the building capacity also a column. Now we don't want to take that. You have to increase to 25 in this case, because your national zero code is 1, but for the UK, for the United Kingdom, the national net is 0.85. So individual is not below than applied strength, so we have to increase it to 30. So in this case is certified for the national net, UK national net. Okay, and for the foreign net is okay when you apply 25 megapascal. But for the decay net in support, so we have to increase here to 30 megapascal. And you can compare the percentage of compression in when you increase the concrete from 25 to 30. This the compression ratio is from here. If you take a revision in before, you can see here for the national net. You can see here the compression ratio is almost 100%. Okay, almost 100% is not a good concept. You have to shoot is below 100%. So you can estimate the our section is certified in the test. Okay, and for the case we may be to the minimum rebar column. This minimum rebar is about 1%, so it is certified for our section. For our shallow for bending we can increase this more, but in the case we can take the 30 only. Megapascal to make sure the compression ratio is 80% is good. Okay, for the column. And now we have start to other one question for the high tech. Okay, for the high tech you agree. design to determine our geometry. Okay, here the spacing of the height or spacing of the driving height from one to another one is the minimum is 2.5 centimeter of height to 4 millimeter of height. It depends on your types working on friction or unbearing, and for the unbearing you have to take it to up to 4 millimeter of height. Okay, so you can check here. This means it stand from here to here, from here to here. It take 2, okay, it take 2.5D, okay, it take 2.5D, it take 2.5D to minimum 2.5D to 240. Okay, the distance is 2, minimum is 2.5D to 4D. Okay, the distance from one pi to other pi. Okay, you see here, the distance from this pi to other pi is minimum 2.5 to 4D. So you can determine the basic geometry on your iPad, and after that you have your dimension of your pi is indicated. You take it 3 multiplied to 300 multiplied to 300 divided by to support this load to take it from sorry for the card, and for the extent, okay, from here to here you can take it, the minimum is 15, okay, 15 centimeter. The minimum is 15 centimeter, okay, from the edge of pi to the edge of the pi cap. So you can determine the length of the pi cap, and for the width of the pi cap you can take here also the minimum is 15 centimeter. So okay, 15 centimeter minimum, but you can take it more higher to 200. It depends on the decision, but for the minimum is 15, okay, 15 minimum, okay, is 15. So after that you will can determine your dimension of iPad. Okay, you have to determine your spacing from one pi to the pi face, and for the height of the pi cap is equal to L divided by 2. In the case we take the length of L from here to here, okay, from here to here we take it the length of L, okay. You can take the length of L only from the axis to the axis, but in the case I want to take for the overall length of the pi cap divided by 2, and it's called it the height, okay, the height. So what is the constraint of your pi cap? The constraint of your pi cap is not greater than the constraint of column, okay, is equal or more or greater than, is equal or greater than the strength of concrete column multiplied with 5 megapascal or 10 megapascal. And how to determine the constraint of pi cap? For the question you have to check the condition in the column at the bottom of column. you have to check this stress of concrete column at the bottom of concrete column. For monitor, you can see my tutorial how to design pie cap. I post in my channel. You can check here how to verify with this condition. Make sure our pie cap is safe when we apply the load within the column within the pie cap. You can check here for the allowable strength or allowable strength of the concrete. Design strength of concrete can receive the apply load. You can check here from our previous tutorial. We have to detail about this design procedure. You can check. Okay, you can check in my previous tutorial. Here you can check. And we talk about single ply for our previous tutorial about how to design pie cap by using starting ply for the cantilever beam, cantilever ground beam. You can check that example is pretty good example. It's a very practical test in construction site. You can check here for monitor. Okay. And now we have to come back, and if you don't know, you can use the constant strength as the minimum at the constant strength of the column. And for the shear stress, you have to make sure the concrete shear stress is the shear stress, the applied strength is less than or equal to the design shear strength as concrete divided by 2, or only 50%. For the code, you can use 0.8 multiply the square root of SCU, or the maximum you use is 5 MPa. Okay, megapascal. For the register method, we are 8110. But for your code, this value not limit, but it will be increased with concrete strength. But in the code, this value is limit only 5 megapascal. So we have another example for determining pie cap geometry and pie cap rebar. Okay, it is very quick view how to design it. Okay, you have to input the rebar property. The strength is 400 megapascal per centimeter. Generally for the rebar is 1.01 or 1.05 or 1.15 for maximum centimeter. Now we can do the maximum centimeter to apply 1.15. And the dimension, we have to determine the returning power. We take it from 75 centimeter to, you can take it to 30 centimeter. I indicate if you only 75 to 10 centimeter internal test. Okay, you can check here. This from your link concrete to the top of cutting pie is around 75. Okay, minimum 75 centimeter. Okay, 75 centimeter or 10 centimeter, and our diameter of the drawing pipe is 30 centimeter. So you can take the spacing of the also driving time from 2.5 to 4 indicate you is 3, and so after you input the review you can determine the lane of R. Okay, lane of R is equal to 3 multiplied with diameter or driving time. You get the review, and you plug with 1 diameter or driving time, and you add for the H distance with 15 multiplied by 2. You will get the length of the pipette. Okay, this is the minimum H is 15. Okay, and if you have to extend 15 from the driving height, you can determine the width of the pipette, and for the effective depth. Okay, effective depth. So we have to use the spacing from 1 pi to the pi divided by 2, and for the height we use this effective multiplied with the bottom of slower. So the effective is 45 centimeter, and the height of the pipette is 55 centimeter. So for the rebar area, you can check in my previous tutorial how to design a curve for the rebar area. Okay, explain comprehensively in this tutorial. You can check it, the striking time method and distributed normal method. This one is economic, and this one is you can apply on your production side. You can see here the result is the same. To determine the angle of the start, to determine the focus starting time, and you can take this focus time and to design it directly. Okay, you can design it. Okay, you can take the force to design the tension rebar at the bottom of high cap from the position. Now I also take from that slide to compute this value, the angle start the direction. So in the case it's not the same with the case because we have a 2 pi support 1 coulomb. So we have to divide the force from the coulomb by 2 to take the action for 1 pi. Okay, now you got the action per pi, and for that you have to design from here, and for pi specifically important to determine the area of the rebar in the pipette. So you can put that. Okay, we got this total rebar, and we use one radio rebar that is noise. One radio rebar is 179.85. Okay, our diameter is 16, so you use 6 dB 16 pieces for our pipette. Okay, okay, you can check here, but in detail we use only 400 millimeter. But for our example, we use high is 55 centimeter. But for the concept applied to the same, you can see in the drawing. Okay, it is our calculated area or rebar. you take it and distribute it in for the long duration, it is very important, and for the short distance, you can use the minimum. Okay, this is the navy bar, and this one, the distributive bar, you can use the minimum bar position, and for the top, you can also use the minimum bar to prevent crack at the top, and sometimes you can leave it, not include it at the top in case you don't care about the continuity at the top of the surface. Okay, so now we have to complete our tutorial from the design and to do 3D dimension. You can check the previous tutorial about how to design, and for this tutorial we will show you how to do 3D dimension for all three elements. You can check from 1 to 1 how to determine the depth of the beam, the depth and the thickness of the slate. Okay, and the column, you can estimate the column and the design in column. Okay, this is very important. You have to check the applied stress at the bottom of column with the resisting or allowable constant stress at the bottom to make sure the allowable is bigger than the applied stress. Okay, and you can compare the compression ratio to make sure the concrete is working more than the bar, so this value is less than 100%. Okay, you can do the minimum with bar in column. In other case, you will be incorrect here from 1 to 2.5% for the column applied for the bending moment. Okay, and for the pie cap, you can determine the geometry. After you determine the geometry, you can calculate it area or the bar easily by using flat incline method quickly. And for the estimate the load for the pie cap, in the pie cap you can take it from this rule assume that I made it for you. You can check it. Basically, you have to know about the total reaction and the total area of your ground slab and the column area, supporting area, and the slab number slab. Okay, you have 10, you can put 10, and number of story is 9. If you put 10, the number of story is 9, and you have to estimate the average load per square meter. This is a very important step. You can calculate it by divide the total area, total load with the total area. Okay, total area. You can see here 4 multiply with the total area of the ground slab. You get the total area of the building. Okay, so you will got the average serviceability per square meter. So you can take this average by divide this. Okay, 1.1 or 1.2.3 is up on your building type. You can apply it from 1 to multiply with the column. Okay, the supporting area column, and multiply with the story. You will get the load for the serviceability. You can take the load to calculate the building quantity on pi or to estimate pi arrangement for serviceability. And for the ultimate load, you can check from here. Okay, from here for the ultimate load is around 99 pounds per column. I can verify it with you by the issue it's correct or not. Okay, you can check here. This value is around 95 pounds per column when you attack. And for our rule, you can check here. It's around, okay, is around 100, okay, 100 town or 99 town is very similar with without any tab, but you can do it quickly by using the method, okay, by using the method, okay. You add the factor 1.425 multiply with the estimated city load, okay. So you will get the ultimate load on the PyTab, okay. Thank you for your watching. For other questions you can ask me directly in the group structure expert, or you can find in the below YouTube comment. I will explain you step by step, and it's hard to understand. We will make other video example about your question. Thank you for your supporting and for your watching our tutorial. Thank you.